All right, welcome to the last lecture of this chapter and of this year. So hopefully you've been watching all these videos. I appreciate you if you have. And this one is on electronegativity. So extremely, really important topic here because basically this kind of boils down to why, chemical reactions take place. Why do compounds behave with each other the way they do? And it all boils down to the electronegativity of the atoms or the compounds that you're looking at. And so electronegativity is a huge concept in chemistry. And so without further ado, let's dive right in to see what we're talking about here. Let's see, I lost my place here. Here we go. So if you combine, like say, for example, oil and water, here's a classic example, and you wonder why, they separate and they don't really are attracted to each other. Well, why is that? There's something about water molecules that cause them, to bunch together in one region, and there's something that causes the oil molecules to bunch together in their region. What's causing that separation to each other and attraction to themselves? And so the best way to understand it is by looking at the water molecule first of all. So the water molecule is the best example of polarity there is. Water, H2O, is one of the most polar molecules we know of. It's extremely polar. And so, in other words, it has this dipole moment where you have a partial negative and a partial positive, and it's almost like it makes the molecule literally like a magnet. All right? And so, basically, what it is the bonds that are there between the oxygen and the hydrogen. They each consist of an electron pair. 2 electrons shared between the oxygen and the hydrogen. Well, the oxygen and hydrogen atoms, they're each going to donate 1 electron, right, to that pair. However, they're not going to do that equally, like most children don't either, the book says, and is a common analogy. The oxygen ends up being like an electron hog, and it's going to take more than its fair share of the electron pair. If you were to take a freeze frame, if you were to take just a quick snapshot of the electrons and where they are, you'd see that most of and then put them all together, like take quick snapshots, like rapid fire, and then look at them all, you would see that most of the time the electrons are here, but every now and then they'll be over here. And then most of the time they're over here, and then sometimes over here. Like the hydrogen, poor hydrogen with only 1 proton, barely gets to have any of its electrons. But the oxygen with 6 protons has a huge attraction to those electrons. And so oxygen is very electronegative, meaning that it is hungry for electrons. In fact, that's a definition. The ability of an element to attract electrons within a covalent bond is called electronegativity. And so for every chemical bond here that you have, for every covalent bond like this, regardless of the atoms, you're going to have somewhat of a degree of electronegativity there, where one atom usually wins, is a little more electronegative than the other. Oxygen is extremely electronegative, and in this case, it's the more electronegative, way more than the hydrogen, which is really low in electronegativity. And so because of that high electronegative and low electronegative, you get a really, really big difference there. It's like a big brother and little bitty baby. And so it's extremely polar. Okay, that means that, again, it has to do with the proton and electron differences. If oxygen technically has 6 protons, but yet it at any given moment will almost have 8 electrons around it, then you essentially have a higher negative charge here. But if hydrogens only have 1 proton, and they really hardly ever get to have any of the electrons, then they're essentially just a positive proton hanging out there. And so they have a partial positive charge there. We use these little symbols, or little Greek symbols. They kind of look like a G. It's sigma. I think that's a Greek letter sigma. Sigma positive and sigma negative. It's like a partial charge. Oh, here it is. No, it's delta. Excuse me. Delta, not sigma. Delta. And you have delta plus and delta minus. And we use those to show partial negative charges or partial positive charges. And basically we need to signify that anytime we're trying to represent this like uneven electron sharing, which again is a vocab word we call the dipole moment. You have dipole, two poles, positive and negative poles. It's basically a separation of charge within the bond. And you know, covalent bonds that have like really, really high dipole moments like this, they're going to be what are called polar covalent bonds. So this is not only a covalent bond like you know where there's an electron sharing, but it's a very polar covalent bond. And now the magnitude of that dipole moment, again, there's going to have some degree to it. There's going to be a degree of polarity in that bond depending on the two atoms that are there, or depending on, better said, the electronegativity difference between the two elements in the bond, all right, and the length of the bond and so on. And so if we just assume a fixed bond length, then the greater the electronegativity difference, the greater the dipole moment. And so here's a nice little table here. I love this. And I'll point you guys to another periodic table that has kind of the same thing but with better values, easier to read. Again, this is just the main group elements. We've left out the transition metals just to keep it a little simple. And also the noble gases, you can see they're still here, but there is no electronegativity. They're already happy. They don't want any electrons. Remember, this is the tendency or the ability of an element to attract electrons is how we measure electronegativity. And so real tall here you can see is fluorine. That is literally the most electronegative element. It has a value of 4.0. Oxygen is 3.5, it looks like. So somewhere in between 3.4 and 3.6. Nitrogen is at 3.0, so it's right here. So the scale goes from 0.7 being the lowest, which is cesium, to 4.0 being the highest. So there's your range, there's your spectrum, okay? And it makes sense. In fact, does cesium want to gain any electrons? No. Cesium is like super, super eager to get rid of that one valence electron that it has that's way out on the 1, 2, 3, 4, 5, 6 energy level, you know? So it's pretty easy to get rid of that electron. So this is kind of the opposite of ionization energy, essentially. There's a low, the way we word it, it's kind of the same. There's a low ionization energy that's required to remove an electron away from cesium. Also means there's low electronegative force because it does not want to gain electrons at all, actually. Now fluorine is really, really eager to gain electrons, so it has a really, really high or strong electronegativity. And now basically the way you do the math is you look at the two elements you're looking at, that you're working with, that are participating in the bond, like in this case oxygen and hydrogen, and you just subtract. So oxygen is 3.5, hydrogen is 2.1. What's the difference? Sorry, I'm scrolling down here to try to see what table they used. What's the difference again then between the oxygen and hydrogen? It's 3.5 and 2.1. That leaves us with 1.4, right? 1.4. So then you're going to take that number and you're going to look at this table 10.2. Table 10.2, anything between 0 and 0.4 is pure covalent. Anything between 0.4 and 2.0 is polar covalent. And that's where we are, right? We're at 1.4. So we're under 2. So we're in the intermediate range here of polar covalent. There's a lot of polar covalent compounds. And then anything higher than 2, well, you're not even talking about a covalent bond anymore. If there's an electronegativity difference but it's higher than 2, you're literally dealing with an ionic compound. In that case, the electrons are just given entirely to the other element. Kind of like table salt, remember? Table salt, the sodium loses an electron completely to chlorine, and chlorine gains it. And then there's just an attraction because you have an ion and an ion that are opposite charges, and so they're attracted to each other. But there ain't no sharing going on there. There is no line we would use to represent a sharing of electrons there, like we would in this case. In this case, if fluorine and hydrogen took their covalent electrons, their covalent shells, and they merged them together, because that's actually what happens, that shell, that outer energy shell, will actually fuse or hybridize with the other outer valence electron shell to form kind of this structure here. Then you would have kind of this shape, sort of. It would be linear, and it would obviously be linear, but it would also be like very polar, because we're not concerned with shape so much in this section as we are the strength of polarity. Remember, fluorine was really high. It was like 4.0, right? 4.0. I don't know if you can see that on this table. If you can't, hopefully you have your book, or I'll show you a periodic table in just a second where you can find better values, easier to read. Fluorine is at 4.0. Hydrogen is at 2.1. That gives us our value at 4.0 and 2.1. That's going to be 1.9. But look, 1.9 is just under 2. So we're technically still a covalent bond, but extremely polar. Extremely polar. Probably even more polar than the oxygen and hydrogen, actually. And so you basically kind of have sort of a continuum. You know, we do our best to draw a line and say, okay, it's at 2.0. Anything higher than 2.0 is ionic. Anything lower than 2.0 is covalent. But what if you're exactly 2.0? You know, it's kind of tricky, right? What if it's exactly? That's why here you can say that it's anything higher than 2.0. They made sure to put that plus sign there. Anything that's exactly 0.4. I remember this from past 2 years. We've run into this discrepancy. You see 0.4 in here, and you also see 0.4 there. What if it's exactly 0.4 is the difference? If it's exactly 0.4, then keep it at pure covalent. Anything higher than 0.4 and lower than 2.0, or 2.0 or lower, is intermediate. In fact, I've actually seen on Google this spectrum changed. These numbers are adjusted a little bit. And it's like, wait a minute, which one's right? And so the point I'm trying to make here is the continuum here is a large continuum. You know, it's a range. And so sometimes we love to put things in boxes and say, hey, anything in this box is ionic and anything in this box, because it makes learning easier. But just to be honest with you, man, this is actually a continuum. And, you know, there's ionic bonds and covalent bonds are they're just bonds. They're both bonds, but they are very different. They are very different in the fact that, yeah, you know, one is the electrons are given or taken away, and here they're shared just unequally. Here they're very shared equally. So if you have a pure covalent, not polar, but pure covalent, then you essentially have a non-polar molecule at all. Like it's a total equally shared electron arrangement, like two identical twins completely sharing their toys. All right. And so here you go. Basically, if you have to answer these questions, like classifying bonds, you basically just need to look at the remember, this triangle means change. This triangle here is the Greek symbol delta En, or the difference in electronegativity. That's all that means right there. The difference in electronegativity. It's just a subtraction problem. So if you were to look at problem here between strontium and fluorine, and fluorine is 4.0, strontium is 1.0. The difference, the electronegativity difference, is 3.0. So if you look at the table, refer to table 10.2, you would see that that's an ionic bond. Or you would just know that, hey, strontium is a metal, fluorine's a nonmetal. Metals and nonmetals come together to make ionic bonds. All right? And then two nonmetals like nitrogen and chlorine, or nitrogen and oxygen, they come together to make covalent bonds. But you can have pure covalent or polar covalent. Like for B, with nitrogen and chlorine, the difference is 0, isn't it? It's 0 because they're both 3.0. Even though they're different elements, they both have an electronegativity value of 3.0. And so it's 0. Basically, you just say it's purely covalent. And C, between nitrogen and oxygen, your answer is 0.5. And so you're actually going to classify that as polar. It's weak, but it's still polar. And before we look at this real quick, the polar and nonpolar bonds, I just wanted to show you that there is an electronegativity periodic table, PDF, chart, whatever, that you can just go on Google, click on images. So you have some selections to choose from here. If you want it in 3D, sure, take one in 3D like this. We got the same values here, right? Remember, we learned in one chapter a while back, I think it was even chapter 9, and so that we're going to test on this, that electronegativity, no, we didn't. This was one of the trends I told you they should have done. They didn't. They did ionization energy, metallic character, and atomic size, but they didn't do electronegativity. They should have. But the arrows go to the right and up is for increasing. Electronegative increases as you go to the right and as you go up the periodic table. And so here's your values. If you want to look at a nice friendly here, if you click on open image and new tab, you can do that and print it, or you can save image as and then save it on your desktop, and then print it that way by clicking on the JPEG. It's up to you how you want to look at that. But I'm going to go back to the lesson here. So now we need to consider molecules. We just looked at one bond. But if you look at like CO2 or water, you got more than one bond there, right? So you have more than one dipole moment that you need to show with arrows, basically. And so if we want to determine whether a molecule is polar or not, then we basically need to determine whether or not the molecule contains any polar bonds. So you kind of have to look at all the bonds, basically, if you want to look at a whole molecule. And then you need to determine whether the polar bonds add together to form a net dipole moment. So that, of course, that was the summary, but let's go back and look at some examples. So if we look at CO2, for example, each carbon double bonded to oxygen is polar, right? This is a polar bond, and that's a polar bond. Because if you do the subtraction is 1.0. Remember, anything higher than 0.4 was polar. So would you say it's polar? No, but it's not. And here's why. Because it has a linear geometry, the dipole moment of one bond then completely cancels the dipole moment of the other bond. Does that make sense? They can like cancel each other out because they're in the same plane. And so this is essentially a non-polar molecule. We can understand this with an analogy. Imagine each pair, I love analogies. Imagine each polar bond to be a rope pulling on the central atom. In the CO2, we can see how the two ropes pulling in opposite directions make the carbon atom not want to go anywhere. So they pretty much cancel out the effect. Sure, this oxygen is trying to pull the carbon atom to the right, but this oxygen is trying to pull the carbon atom to the left with the same amount of force. Because look, we have the same bond. Now, what if one of these bonds was different than this bond? Well, that'd be a different story. Because then you'd have like a stronger person on the left than on the right, or vice versa, a stronger person on the right than the left. So as long as the two bonds here are equal in an amount of a electronegativity difference, and they're in the same direction like this, in the same plane, they'll cancel each other out. And so we can also represent, the easy way to do this is, you remember, you can represent these polar bonds with arrows, which we call vectors, whatever. You don't have to draw these arrows, by the way. I don't care. I won't have you doing any problems where you draw the arrows, but they do help you to see it. If you have your Lewis dot structure drawn and you really want to figure it out, you can draw yourself these little arrows, and they kind of help. Or the little positive symbol here. It's like an arrow where you put a little plus at one end where the polar is plus, and a little triangle here on the arrow tip where your partial negative charge is. And so you have your partial negative, your partial positive. You have all your arrow vectors, and you can kind of see, which direction are the arrows going? Are they in the same plane? And then yet in opposite directions? Well, then there you go. Those are going to cancel each other out, assuming they're the same strength. So you might even want to put like the little value there or whatever. So let's look at some common cases of adding dipole moments to determine whether a molecule is polar. But before we do that, in summary, we need to remember that if you're determining whether, because I'm going to add this, a lot of students get confused every year when I do this. I don't know why. I ask them to determine the polarity of a bond. Let's say like between, or I'll give a molecule. I'll give a molecule like this, and I'll say determine the type of bond between carbon and oxygen in this molecule. Well, that's polar. The bond there is polar, but the molecule is nonpolar because both polar bonds are canceling each other out. Does that make sense? So I can ask you about a bond, or I can ask you about the whole molecule. And so in summary, if you're trying to determine the polarity of a whole molecule, you need to analyze every single bond in the molecule and see, do those vector arrows cancel each other out or not? And so, for example, two identical polar bonds pulling in opposite directions will cancel, just like we showed. Same here. Three identical polar bonds, they can all three be polar, extremely polar. But guess what? If they're polar at the same strength and they're pulling in opposite directions like this at 120 degrees from each other, then the molecule will be nonpolar. Okay, now what about this situation here, though? The trigonal pyramidal. If you have three polar bonds in a trigonal pyramidal arrangement, then they will not cancel technically. They will not technically cancel because you would still have like an electron, a lone pair of electron pair here. Remember, that's actually what's repulsing these atoms, pushing them down. So that lone pair of electrons there kind of messes up the whole, situation there. And so likewise here, when you have two polar bonds with an angle of less than 180, like you have a bent molecule, then they're not going to cancel. Okay, they have to be exactly 180 like this up here for them to cancel. If they're a little bit less than 180, like a bent molecule, they're not going to cancel. Sorry. So this molecule would be polar as well. And the reason this would be bent anyways, as you know, is because there would be a lone pair of electrons on this central atom pushing these electron groups away, making it bent. So if you have a lone pair of electrons here, there, then that's totally messing up the cancellation, right? Even if these did kind of cancel each other out with the same number or whatever, they're not going to because of this electron pair here. As far as the whole molecule concerned, it's polar. Again, four identical polar bonds in a tetrahedral arrangement, as long as it's tetrahedral like this and they're all four the same atoms, then it'll work. But if you have hydrogen, 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 and oxygen, then they're different strengths, aren't they? The oxygen, and let's say this was carbon in the middle. In fact, do we have an example of that? Maybe not. If we had carbon in the middle and oxygen, that would be a different polarity than the carbons and the hydrogens that would be here. All right, let's look at ammonia. Ammonia, this is perfect. This is the example I have on my wall there. If you've noticed, NH3. And guess what? All the nitrogen to hydrogens have the same polarity. So it seems like they would cancel each other out, but that lone pair right there is messing it up. So it's technically not polar. So it is polar. It is polar. They don't cancel each other out, making it nonpolar. They don't cancel each other out, so it makes it polar. If they did cancel each other out, it would be nonpolar. But now, this is really interesting here. Wish we had time to do this project this year, but we'll do it next year in organic chemistry and biochemistry, the way a soap molecule works. So soap is really cool. You basically take a grease or a fat or an oil, something like this that's nonpolar. So a bunch of carbons and hydrogens and an oil or a lipid, and then you react it with sodium hydroxide, which is a base, and it ends up putting a sodium here and an oxygen, which makes this head polar. So soap is actually both. So yeah, we start to get into a little muddy water here. Like I said, when we analyze the polarity of a molecule, we don't necessarily look at the whole molecule always. Sometimes we look at regions of a molecule. And soap is a really awesome molecule because it has a long non-polar tail, with very equal distribution of carbons and hydrogens. So they're sharing their electrons equally and in the right angles, with all those angles canceling each other out and such. But over here you have an oxygen and a couple extra carbons. Well, that is there's no polarity right there. The oxygen right there, and it even has an extra electron there, you would see after the reaction. And so with a polar head, it allows it to be soap is attracted to water. But soap is also attracted to other nonpolar substances, because nonpolar substances also like other nonpolar substances. So when you wash your hands, whether you're trying to break away oil or you're trying to break away a bilipid membrane of an organism or a virus, viruses are not living organisms, but they have a bilipid membrane, and that's nonpolar, and it's a lipid. And basically the soap will be attracted to the membrane of the virus, and then it'll take it away from your hands, but then you still got to get it down the drain. And so that's why the polar head makes this attracted to water. Otherwise the water would not be attracted to the nonpolar virus or an oil. If you have oil in your hands and you try to wash it under the sink, not going to happen, because water's polar and oil is nonpolar. But if you take oil and you react it with sodium hydroxide, which is a strong base, you can make a soap molecule. Making soap is actually really fun. And you can use different oils like olive oil or coconut oil, or different oils that have different properties because the carbon links and how many double bonds would be present or whatever. And then, yeah, I'm going on a tangent here. Sorry, let me keep moving on here. I don't think there's anything else to say about that. Basically, you just have to be able to identify and answer those problems. Remember, the key is, am I asking about a certain bond, or am I asking about the whole molecule? You have to read the problems carefully when they're asking you to determine the amount of polarity, whether it is polar or it's not polar. So be careful there. And thank you again, as always, for watching this video. Bye-bye.